Alright, so in this tutorial, I'm going to teach you how to prove the legitimate condition in a Bernoulli distribution. So let's start. So a random variable x is said to follow a Bernoulli distribution with parameter p, where p is the probability of success and q, which is equal to 1 minus p, the probability of failure. Okay. Now let's take note that in a Bernoulli distribution there are only two outcomes. Okay. So it's either the outcome is a success, that is when x is equal to 1, or the outcome is a failure when x is equal to 0. So it means that in a Bernoulli, s can either be 0 or 1. So x takes only two values. Okay. Alright, so now let's look at the probability mass function, PMF, of a Bernoulli distribution. Now we are using PMF because the random variable x in the Bernoulli distribution is a discrete random variable. Okay. So it means that the PMF, which is P of big X is equal to small x, is equal to P to the power x 1 minus P to the power 1 minus x. Okay, where x runs from 0 to 1. Okay, so now our duty here is to prove the legitimate condition in the Bernoulli distribution. Okay, so for legitimacy, it means that the sum of the PMF from 0 to 1, that is P to the power x 1 minus P to the power 1 minus x, should be equal to 1, and x takes values 0 and 1. Okay, now because we are summing from 0 to 1, it means that our summation of P to the power x 1 minus P to the power 1 minus x from 0 to 1 can be written as this is what I'm trying to say. I'm saying that you can write this whole equation, okay, as P of x is equal to 0, because we are starting with 0 first, okay, plus probability of P of x is equal to 1. And we want to show that if we add P of x is equal to 0 and P of x is equal to 1, you're supposed to get 1. Okay, so this is what we want to prove. Now, because we want to show that P of x is equal to 0 plus probability of x is equal to 1 is equal to 1, we first of all have to calculate for P of x, probability of x equal to 0 and probability of x equal to 1. Then after that we add the 2 and check to see if we'll get an end result to be 1. Okay, so now for P of x is equal to 0, it means that we pick up the PMF function, and wherever we see x, we are going to substitute 0. Okay, so let me start this way. Originally, our PMF is P of x is equal to small x, which is P to the power x 1 minus P to the power 1 minus x. Alright, so we want to find P of x is equal to 0. So it means wherever we see x, we are going to substitute 0. So P to the power 0, 1 minus P, 1 minus 0. Okay, so this will end up giving us P to the power 0 is 1. Okay, 1 minus P to the power 1 minus 0 is this. Okay, we'll end up getting 1 minus P. Okay, so it means that when our P the probability of x equal to 0 will give us 1 minus p. All right, so now let's calculate for that when the probability of x is equal to 1. Okay, so for probability of x is equal to 1, we're going to do the same thing, but this time around we are going to substitute 1 for every place we see x. Okay, in every place we see x. All right, so 1 minus p, 1 minus 1. Okay, p to the power 1 is p. 1 minus p to the power 1 minus 0 turns this way, and we're going to get 1 minus p. 1 minus p to the power 0 is 1. Okay, so we end up getting p. So it means that p of x is equal to 1 will give us a final answer of p. All right, so we are going to add this to p of x is equal to 0. Okay, so have in mind that that we want to show that p of x is equal to 0 plus p of x is equal to 1 will give us a final answer of 1. This is what we are after. Okay, so kindly take note of this. Now we've been able to find p of x is equal to 0. So p of x is equal to 0. We had p. Okay, so let me write it. P of x is equal to 0 plus p, probability of x is equal to 1. P of x is equal to 0 give us 1 minus p, and p of x is equal to 1 give us p. Okay, so it means we end up getting 1 minus p plus p. Okay, so minus p plus p will give us 0. So our end result is 1. Okay, so it means we've been able to prove that p of x is equal to 0 plus probability of x is equal to 1 is equal to 1. This implies that if we should sum the PMF, we have to get 1. All right, so this proves the legitimate condition under a Bernoulli distribution. Okay, so I hope this lecture was helpful, and kindly check our playlist to get more videos, and do not forget to subscribe. Can you also press on the bell icon so that you don't miss any updates from Co-Prime Statistics? Thank you very much for watching.